Hello everyone, welcome to my YouTube channel. So in the first tutorial of molecular dynamics simulation, I explained the basic concept of molecular dynamics and also introduced you with the force field. In this video, I am going to show you different model of force field and I am going to explain the basic concept of numerical integrator and time step using molecular dynamics simulation. So you already know that force field is a collection of equations to calculate the potential energy present in each atom of a molecule. Okay, so the source of potential energy of any atom is the chemical bond, the bond length, bond angle, dihedral, that means different bonded interaction, and non-bonded interaction like van der Waals interaction and electrostatic interaction. So force field calculate the potential energy. So this is the basic concept. Okay. So here is a list of few force field model like amber, charm force field, Gromos force field, OPLS force field. Few other force field are also there. They are conceptually similar, but their equation is slightly different to accurately calculate the potential energy of atom. Okay, so equation is slightly different but the concept is similar. Okay, all of them calculate the potential energy, that means they vary in functional form. Okay, you know the equilibrium bond length. So in charm force field the equilibrium bond length may be 1 angstrom, but in case of amber force field it may be 1.03 angstrom. So that is the difference. Okay, uh, just and sometimes the simulation target is also different, like amber force field is more suitable for DNA RNA by this kind of biomolecules, and charm is more suitable for protein ligand complex or protein. Okay, so when you are going to perform molecular dynamic simulation, you have to choose force field for your biomolecules. So it's better to go through different research articles so that you can choose suitable force field model for your simulation for your biomolecules. Okay, but conceptually they are all similar. And amber force field usually coupled with amber molecular dynamics simulation package, and charm force field usually used in GROMACS. Other force field is also used, but charm 27, charm 36 are the mostly used force field in case of protein ligand simulation. Okay, so main thing is that the force field calculate the potential energy of each atom. Now this potential energy is converted into the force which act on each atom. Suppose we are trying to simulate this molecule, okay, this organic molecule, and this organic molecule contain 10 atoms. Okay, and the position of this carbon atom is r at t time. That means suppose now time is 1 nanosecond and r is the position or coordinate of this carbon atom. Okay, so when it start moving, that means we start simulating. Okay, this carbon atom will change its position because some force is acting on it, because it has some potential energy. So this is the force, amount of force which is acting in this carbon atom. Okay, therefore this carbon atom changes its position to this new position. Okay, from this position to this position. So this is the position of this carbon atom at t plus delta t time. That means initially the time was 1 nanosecond, and suppose after 2 femtosecond, the time is 1 nanosecond plus 2 femtosecond, and this is the new position of this carbon atom. So r in t plus delta t time. Okay, so now we know the amount of force. We can calculate this force from the potential energy. That means through force field we can calculate the force. we know the time, that means it's 1 nanosecond. R is the position or coordinates of this atom, and we also know the mass of carbon atom. Okay, and this is the delta t time step. So if you want to see the position of this carbon atom after delta t time, okay, so you know the time step, that means you want to see the position after 2 femtosecond. So the new time will be 1 nanosecond plus 2 femtosecond. Okay, so in new time, this is the position of this carbon atom. So through this equation, we can calculate the new position of this carbon atom. Similarly, for each atom, we can predict or approximate their new position, because we know their potential energy, the force, the time step, their mass, everything we know. Therefore, for each atom, we can approximate their new position. That means we are using the Newtonian rules or Newtonian equation to approximate new position. Suppose you are simulating this molecule over a period of 1 nanosecond. So 1 nanosecond means 10 lakh femtosecond, that means 1 million femtosecond. Okay, and if the delta t, that means time step, is 2 femtosecond, that means you are trying to approximate the position of each atom after every 2 femtosecond. And if total 10 atoms are there, so this equation will be solved, if I am not wrong, for 5 million times, because 1 nanosecond, that means after every 2 femtosecond we are solving this equation, and for 10 atom, because this molecule contains 10 atoms, so we have to calculate or we have to solve this equation for 5 million times. So that's why it is known as numerical integrator. So what is a numerical integration or integrator? It's the equation which is solved numerically at discrete time step to determine the trajectory of each atom. That means we are trying to assess or approximate the new position of each atom. Okay, that means we are continually solving this equation. It's a repetitive procedure. Okay, that's why it's numerical integrator. So target of this numerical integrator is to approximate the position of any atom at a given time in terms of the known position at a previous time. So after before 2 femtosecond the position of one atom, and after 2 femtosecond we approximate the new position of that atom. Similarly, we approximate this position change for each and every atom present in a molecule. If the molecule size is very large, suppose in case of protein molecule, several atoms will be there along with water molecules, more than 10 lakh molecules. So for each atom we have to calculate or we have to integrate. Okay, so varlet scheme algorithm or velocity varlet algorithm or leapfrog algorithm, these are the numerical integrator. Different equation, these are the modification of this previous equation, and this is for the varlet algorithm. Okay, some modifications are done in case of velocity varlet algorithm and leapfrog algorithm. These two algorithms are commonly used GROMAC software. Okay, so when you are going to perform your molecular dynamics, then you have to choose this kind of algorithm. So that's why I am showing you. Okay, now let's discuss about the time step in more detail. Okay, so molecular dynamics simulation is actually like a video. That means we are recording, video recording the events which are going on in molecular level. Okay, so it's like a video, and you know the video is actually a series of still photographs. Okay, that means different frames, so or different snapshot. Okay, so if we play this series of frames or snapshot, it will be converted into a video. So you see this video, that means this girl, cartoon girl is dancing, it actually consists of 6 frames, and each frame, its orientation is different. Okay, now if we play these photographs one by one, then it will turn into a video. Similarly, in case of molecular dynamics simulation, what we do after a series of, so after taking a series of snapshot, we play this, and this still photographs is converted into a video. That means we get the trajectory of each atom. Okay, now if this frame number is very low, suppose if the frame number is 6, then the resolution of the video will be low. Okay, but if you take more snapshot, we take more frames, the resolution will be increased, the quality of the video will be increased. Okay, and if the frame number is very less, we cannot capture all the events which are going on. Okay, and if we take more snapshot, okay, all the events which are going on will be captured and it will be displayed in video. Okay, so it is very important to choose the time step. Okay, so how to determine what will be the suitable time step? So you see, these are the different time scale. Okay, you see, for protein subunit association, protein folding, so for protein folding it takes time in second. Okay, for subunit motion it's millisecond, for fast protein folding it may be in microsecond, or for loop motion or torsional angle motion it's actually in picosecond level. And the event, that means the bond stretching, it takes time in femtosecond level. So if you want to capture all the events, okay, so we have to select a time step which will cover all the molecular events, all at atomic level, even the bond stretching. Okay, that's why the time step is selected 1 femtosecond to 2 femtosecond. Okay, so this is about time step, and that's all for this tutorial. In next tutorial I will explain few other terms, and it is very necessary to know about this term, because when you are going to perform molecular dynamics simulation, several parameter file will be there, and uh, you should have the ability to understand the different parameters. Otherwise you will not be able to perform the molecular dynamics simulation. So step by step I am going to introduce you with the different kind of terms which are used in molecular dynamics simulation, different file formats, everything will be explained in step by step. Okay, so that's all for this tutorial. Thank you for watching.